next talk is Fabio. That is about generalized quotients and holographic tools.
Okay. Well, thank you for putting together this conference, especially to Jonathan and Miriam. And thank you for showing up on the last day. And it's been a pleasure to be back in Philly after many years. So to celebrate, in order to celebrate this, I'm going to talk about something that I started thinking about more or less around that time. It has generalized in a title, but it's not about generalized symmetries. So it's something else, and I hope I will show you what this something else is about. And this is a work that appeared at the end of the year in collaboration with Oren Bergman, Ichor Kim, and Christoph Uhlemann. Good. So what is about? It's about a different corner of the F-theory type 2B landscape. And in particular, it's about 60 ADS or ADS6 solutions of type 2B supergravity. So these solutions are known. I mean, some of them are known. Many of them are known. And they are dual to 5-dimensional superconformal field theories via the SCFT. They are near horizon limits of the 2B 5 brane webs that we study when we want to geometrically engineer brane engineer the 5D CFTs. They have a non-trivial axial dilaton profile, this solution. The 5 brane sources have been incorporated in this solution, and also the 7 brane sources, the perturbative one, are known, for example, D7 and O7. And in general, they enlarge the landscape of type 2B vacua. So these are not Minkowski 6 vacua, but they are ADS6 vacua. Good. So this is what we know so far. And the main question that arises more or less around that time was that, can we address the following challenge? And the following challenge is to incorporate in these solutions non-perturbative F-theory 7 branes. With non-perturbative F-theory 7 branes, I mean the branes which have E6, 7, 8 gauge symmetry, or also the one that have H0, 1, and 2, or also denoted by this singularity type. So the motivation for this is, solving this challenge would basically solve a personal non-standing challenge that I had. So whether there are ADS6 F-theory solutions. And in particular, they will lead to some new construction on 5D CFTs. These are not always new 5D CFTs. Sometimes are just other description of 5D CFTs that we know. But these are, on the other hand, they're new construction. And finally, these 5D CFTs will generically not have a gauge theory description at low energy. So having the holographic description would be helpful in order to compute, something meaningful, something physical about these CFTs. So this is a brief outline. I will review the holographic setup. I will talk about the brane webs which generate these new symmetries, and then I will these new backgrounds, and then I will come back to the near horizon limit of them. And at the end, if there is time, I will talk about some observables that you can compute from this holographic construction. So the holographic setup. The strategy is pretty standard. So the strategy that one has to adopt is to classify this solution is to solve the supersymmetric equations of motion of type 2B. And the ansatz that you put is a ADS6 work product with an internal space which is M4. And you have to determine this M4, and this M4 will be determined by the supersymmetric equation. Good. The first attempt to the classification was done in this paper with these very nice people around 2014. And the outcome of this classification is that the general feature of this 4-dimensional space is that you have a 2-sphere fiber over a disk. And this is consistent with the isometry. So this is consistent with the R symmetry of the dual 5D n equals 1 CFTs, which is SU2. And the fact that there is an S2 fibration over a disk means that there is an SP1 isometry in this geometry. Good. But if you are a bit more clever, as it was done in this paper and also later with another kind of ansatz in this paper, you can actually impose from the beginning this type of ansatz that the 4-dimensional space has to look like this, where you also impose that sigma is parameterized by, it's a complex surface, so it's parameterized by some holomorphic coordinate. And if you do this, you get a very nice explicit classification of this solution. So you get very nice explicit solutions that you can use and understand what they are. Good. Let me just show you how this solution look like. So they're very nice, but they're still a bit complicated in the way they are formulated. So the metric is a word product of ADS times this 4-dimensional space, which is an S2 fibration over a complex plane where W are the over a disk where W are the coordinate of the disk. And this function F6, F2, and rho will depend on two holomorphic functions, A plus and minus, and their derivatives. So with this dependence, I mean also the dependence on the derivatives with respect to W. The rest of the field is the dependence of the rest of the fields is similar. So we have the free form flux, which is the combination of H free and F free. It depends on A plus and minus as well. Tau has a similar dependence, so it's varying on the disk, and F5 is equal to 0. And what you get is that also the S2 has to collapse at the boundary of the disk. So we want a space that is closed. So we don't want a non-compact space. We want a closed space. And moreover, the differential of A plus and minus can have some pole at the boundary. And the way we interpret this pole is that they generate, basically, they are 5 brane sources at the boundary. And indeed, you can compute F3 close to the pole at the boundary. And what you get is this expression, which is the correct source for the 5 brane, for PQ5 branes at the boundary, where this volume of free cycle is a free cycle, which is a free sphere surrounding these punctures, these poles. So a free sphere is basically this small interval, which is a semicircle around the puncture, times the S2, the fiber S2 on this small semicircle. All the non-trivial information about these symmetries are captured by this disk. So the disk basically captured the full information about these solutions. I keep saying symmetry, but solution. Good. So what is the interpretation of this solution? So indeed, they are near horizon of the 2B brane webs. So suppose that you have this web. So it's you have a web in a 2-dimensional R2. So it's a grid of NS5 and D5 branes. And you can take the near horizon. Imagine that you take a big disk, or well, actually a small disk around the center. And this disk will intersect the 5 brane, the semi-infinite 5 branes at this point. And this will indeed correspond to the puncture that you generate in this solution. So this is the interpretation. But the more correct interpretation is that what you have to look in the near horizon geometry is that you have a sort of R5, which is given by the R2 of the web, so the web plane, and the R3, which is the orthogonal part to the full 5 brane system. So the 5 brane will be, of course, 6-dimensional objects, so they will intersect in this plane, and there will be 3 dimensions which are orthogonal. So you can take the space near the horizon of this web and in radial coordinates, and this will generate this sort of M4, which you can also think about the M4 as a sort of 4-dimensional sphere, which is punctured by the fact that you have 5 brane, semi-infinite 5 brane intersecting this 4 sphere. And you can add 7 branes. Suppose that you have a 7 branes on which the D5 end, in the web like this. And what happens in the near horizon solution is that you have now a source, a 7-brane source or a puncture in the interior of the disk, and together with a monodromy cut, which is the right thing if you have 7-brane sources. Okay, in order to determine the type of 7-brane that you have, you need to compute the monodromy of tau around this 7-brane locus, and you can do it. And you take the solution, and the solution there will be a monodromy if you go around this puncture that is a monodromy for tau, and you can read it off from the solution. But the way you read it off from the solution is that the SL2R action on tau will correspond to a SU 1,1 action on these two functions, which generate the full solution, and you can map A and B to U and V by using this formula. Good. And moreover, if you look close to the 7-brane locus, you can also realize that basically for a D7 brane, you can really go close to the locus where the 7-brane is, and the metric will look like a flat 7-brane solution, where the Minkowski 8 is basically the role of Minkowski 8 is now played by ADS6 times S2, where the 5-brane basically, which are the dimensions that the 5-brane wraps, the 7-brane wraps. Good. What about the 7 planes? So 7 planes were incorporated in this paper. So you can consider a solution which has a reflection symmetry. So in this case, so let's just focus on the disk, which is the important object that specifies the solution. You can take this disk, and this is symmetric under reflection, up and down, and which is a pi rotation of the disk. And now you can take the 7-brane together in this way. And what you can do is you can quotient now this solution by a symmetry of the solutions. And a symmetry of the solution consists of a pi rotation together with an SL2Z transformation. In this case, it's a minus identity, the SL2Z transformation, because when you transform, when you do the pi rotation, the function A will also change. But in order to compensate the transformation, we have to apply this SL2Z transformation. And if you do that, if you do this, what you generate, it's a Z2 fixed point. And moreover, it's in this case, you generate an O7 minus at the center of the solution. And these two branch cut on the left and the right are identified. So what you generate is really a sort of cone by identifying these two sides of this semi disk. Okay, this is the way how you generate the O7 minus plane. So if you are not bored by now, you might have noticed something. So what we have done in this case is a quotient that involves a symmetry of the web together with an SL2Z transformation. So what is this? I mean, we have seen this already in recent year, and we have seen this already in this conference. So, and indeed, what this corresponds is to S-fold. So the S-fold have been studied in different 4-dimension, but also in 3-dimension in this list of paper. But this is a sort of, new example where this S-fold quotient appear. Okay, so let me talk about S-fold quotient of 5D CFTs. So this quotient was studied in the context of M theory, but also 2B brane webs in these papers. So these are 3 papers that appear in 2021. And the strategy, so I will focus on the 2B side. So there is also a M theory version of this quotient. So, and on the 2B side, it really looks like an S-fold, because what you do is you quotient by a ZN symmetry of the web plane, and you also combine this with the action of an SL2Z transformation. In particular, the same discrete as the discrete, so the ZN symmetry that the web plane will correspond to the subgroup of the SL2Z transformation that you quotient by. And this procedure will indeed lead to fixed point at the center of the web, where this this action will have a fixed point, and this will be interpreted as a 7 brane. So as an example, you can take a Z3 quotient of T4. So you T4 as a all Tn have a Z3 symmetry, so you can quotient by Z3. What you're left, it's 1/3 of the brane web in this way, but at the center you have a fixed point that is interpreted as a new 7 brane source at that center, and the conical deficit is indeed compatible in this case with the E6 7 brane. So you can then, of course, separate the E6 7 brane in terms of ABC brane, and what you get is this new web, and then you can also take out this brane by Anani-Witten moves to read off what is the theory. So one thing that is very important in 5D CFTs, and one method that we have to study with, that we have in order to study these 5D CFTs, it's the prepotential. The prepotential basically governs the dynamics of the theory in the Coulomb branch. So it's an effective, so it governs the dynamics of the effective field theory in the Coulomb branch. And the way that the prepotential transformed by this quotient is just 1/n times the prepotential of the original theory, where you also have done the identification of the Coulomb branch parameter, because when you do the quotient, also the Coulomb branch parameter will be identified. So the 1/n factor indeed comes, so you can compute, so for example, you can compute tension of the magnetic strings in 5D in the Coulomb branch, and this will correspond to the area of the compass surfaces of the web. And if you compute the area of the new web is 1/n the area of the parent web, and this is why the 1/n factor comes about. And moreover, the Coulomb branch scalars are indeed identified by the quotient, because you take, for example, T4, and then what you get is basically a rank 1 theory, because you have a rank 3 theory, and the free Coulomb branch parameter get identified. They get identified. Good. So indeed, this was the example that I was talking about. So what you can do in this example, you can take out all this brane, and you can realize that this will realize indeed the brane web for SU2 plus 7 flavors. And from the prepotential, you can check these. You can take the parent theory prepotential, you can apply this formula, and what you get is the prepotential for the SU2 with 7 flavors. And of course, you can also generate by other quotient, for example, taking the quotient of the SU2 zero theory, the Z4 quotient, which has, I mean, the SU2 brane web as a Z4 symmetry, you can quotient by this Z4, and what you together with an SL2Z transformation, and what you get is an E7 7 brane at the center. And indeed, if you do Anani-Witten moves, then what you get is SU2 with 6 flavor on this side. And you can also do the same for this theory for SU2 plus 2 flavors, and the Z6 quotient is as a Z6 symmetry. The Z6 quotient will generate the E8 7 brane at the center, and you can check that the prepotential matches with the theory that you get by doing an Anani-Witten move once you split the brane in ABC 7 branes. Good. But okay, the authors of this paper might hate me now, but there was some tension between these two papers. Maybe there wasn't a tension for them. Maybe it was a tension. There was some mismatch between the result of these two papers, and in particular, some solution or some construction that were taken in this work were not considered in this other work. Namely, that the S-fold that this paper defined was not consistent with the S-fold with this paper was proposed. But it turns out that they are both correct. And that's what we actually solved in one of the puzzle that we solved in our paper, is that these quotients that were not allowed, that were considered in this paper, were not allowed in this paper, are basically n-1 over n quotient of the brane webs. Let me tell you how this will appear. So instead of just so you quotient by the same symmetry, but instead of taking the 1/3 part of the web, you take the 2/3 part of the web in this case. And this would be 3/4 part of the web, and this would be 5/6 part of the web. And the singularity that you get at the center, which is compatible with the conical deficit that you have of the brane web at the center, is indeed consistent with the H0, H1, and H27 brane. And you can compute the prepotential. The prepotential now will be quotient by 2/3, 3/4, and 5/6, and you get indeed the resulting theory that are consistent with the brane web after you do an Witten moves. But for higher rank, the naive prepotential formula doesn't work. So with naive prepotential formula, I mean you take the prepotential for the quotient, and you which is the multiplication of n-1 over n, where n can be from 2 to 6 apart from 5, times the parent theory. And this does not work for higher rank theories. Higher rank, for example, if you do the quotient, the Z-free quotient of T5, and you apply this formula, this will not correspond to the right prepotential. And in order, so we need to really define this quotient better. So in order to better define this quotient, what you have to do is you take n-1 copies of the parent theory, and then you take a symmetry of these n-1 copies, which can take you from one copy to a different copy. So you quotient by this symmetry together with a corresponding SL2 transformation. So the Z-free, for example, for T5, you can take 2 copies of T5, and you can do a Z-free action on 2 copies of T5. And you can see here that the Coulomb branch parameter will be mapped from one copy to another copy. So this is the general mapping of the Coulomb branch parameter under these symmetries. And the general formula for the prepotential follows this definition. Namely, that f of the resulting theory is the 1 over n times the sum over the prepotential of all the copies with the identification. So you have to identify the Coulomb branch parameter as according to this symmetry that maps these Coulomb branch parameters, and then you plug this into the formula, and what you get is the correct formula for the prepotential. And then you can go ahead and check. And indeed, if you do the 2/3 quotient of T5, what you get after an Witten moves is the brane web for SU4 plus 10 flavors, and the prepotential formula, the new quotient formula, will work indeed in this way, and you indeed get the prepotential for the SU24 with 10 flavors. Good. Okay, I mean, so this was the setup for 2 brane webs, for 2B brane webs. So let's go back to holography. And now it's kind of straightforward to generalize the 07 procedure in order to actually generate these new solutions. So what you have to do is to quotient the solution by a symmetry of the solution, which involves a symmetry of the disk that you have times a Zn, a subgroup of SL2Z action, with n equal to 2, which was the 07 case, 3, 4, and 6. And so this will lead to fixed point on this disk. And the way that this comes about is that, for example, you can take Tn. Tn has a Z-free symmetry. You quotient by this Z-free, so you quotient by you quotient the disk by Z-free, and then what you get together with an SL2Z transformation, in this case a Z-free subgroup of that, and what you get is the monodromy at the center for the E6 7 brane, where the 2 sides where the branch cut lies are identified. So what you get is really, instead of a disk, is a sort of cone, because you have a conical defect. You have a conical deficit at the center. And indeed, you can compute the deficit angle, and it's consistent with the 7 brane being 6. You can do the same for other solutions. For example, the grid solution, which has a Z4 symmetry. So you can quotient by Z4, and you can then also apply the SL2Z transformation in order to really quotient by a symmetry of the solution. And what you get is the E7 brane for the grid, if you quotient by Z4. And for this more complicated theory, which has a Z6 symmetry, you can quotient by Z6, which is a symmetry also of the disk of the solution. And what you get is at the center a 7 brane, which is the E8 7 brane. And this solution can be seen as F-theory solution in this way. What you get is ADS6 times, which is actually a word product of ADS6 times M4 times T2, quotient by Zn. So this is the Zn quotient that we are talking about. And more or less, this 4-dimensional space can be viewed as a 4-puncture sphere. So in this sense, this can be viewed as F-theory solutions. Good. So, and we can also generate the solution with H0, 1, and 2 brane. So what you have to do is basically you have to take 2 copies of the original holographic dual. So you take 2 copies of the disk, and then you quotient now by Z3. And what you get is a different deficit angle with respect to the E6 case in this case. And so this was the dual for Tn. And what you get is a bigger section of the pi. So a smaller deficit angle, and this corresponds to the H2 brane. And a similar thing can be done also using for the quotient of the grid, so the dual solution of the grid. So in this way, so you can quotient by Z4. If you quotient by Z4, you get 3/4 section of the disk, and the deficit angle will be reduced. In this case, would be pi over 2. And also, you can do the same for this solution. And what you get is you do a Z6 quotient of this solution, and actually of 5 copies of this solution. In this case, we're 3 copies of this solution. And what you get at the end is a bigger, with respect to the E8 case, it's a bigger part of the disk. Good. So you can generate also the solution with H0, 1, and 2 branes, 7 branes in the center. Good. Okay, let's go over some observables with which can compute by using these solutions. So observables of the quotient theory are related to observables of the parent theory at large N. So in this case, you can compute holographic observables, and one holographic observable that, so the first holographic observable that is usually computed is the free energy. So the free energy is computed holographically by the supergravity on shell action, and the supergravity on shell action is proportional to the volume of M4. And this will be a good estimate of the number of degrees of freedom of the theory. So F5, so this is the free energy. So this is the node F5 S5, because in the dual quantum field theory or the dual CFT, what you do is you compute the 5-sphere partition function, and the leading order contribution of that will be going like n to the quarter in this case, or n to the 4 in this case. And the free energy for the resulting theory is the 1/3 quotient of, so in this case we have Tn over Z3, and the resulting free energy is the 1/3 of the free energy of the parent theory. For the 2/3 quotient, what you get is 2 times the free energy for Tn mod Z3. So this is basically almost consistent with the quotient of the prepotential, because so for other observables that you can compute are, for example, central charges. So central charges will be proportional to the free energy, and this is the central charges will be appearing in the stress energy tensor correlation function or 2-point function, and or flavor symmetry current 2-point functions. And this is you can relate these central charge into F5, and the central charge will be proportional to S5, and they also will be divided by 1/n. So theoretically, the free energy is computed by localization on the phi sphere, and the matrix model that you obtain from localization takes the form of an integral over the Coulomb branch, which involves the classical prepotential. And these will also have other contribution in general, but at large n, these contributions are suppressed. So the leading order contribution is just the classical prepotential. So even if we don't know the low energy gauge theory description of these theories, we can use the fact that we know the prepotential, because we know that the prepotential is the quotient of the parent theory. And so we can compute and we can match the free energy computed holographically, which is the volume MF4, or the on-shell action, the supergravity on-shell action, with the leading order QFT computation by using this quotient prepotential. And indeed, this matches, so giving us a good test for this solution to be dual to 5D SCFTs. Okay, so let me conclude. So we have constructed a 6D ADS solution with F theory 7 branes, and this construction goes via this S-fold. So we quotient by asymmetry, and we also apply an SL2Z transformation. Moreover, we have defined a generalized S-fold procedure, which takes multiple copies of the parent theory and then quotient by the discrete symmetry. And we have computed holographic observables for these theories. And some outlook. So one aspect that we started discussing is that can we generalize or actually apply the generalized S-fold construction to 4 dimension, for example, to generate new S-fold theories. So we know that at lower rank, we basically know all the n=3 theories, but these might be generating new theories at higher rank, or even for any other kind of S-fold, like n=2 S-fold or n=1 S-fold. So, but it's interesting maybe to apply this generalized procedure also to lower dimension to see whether this will lead to new theories. And finally, to come back to symmetries, it would be interesting to study generalized symmetries for these theories from holography. So thank you for the attention.
So, probably one of the things you could do is introduce more than one, say, H277 into your brane web, and so you find out the web is really two wedges each of them, so that will one set. You can do that more than once.
Yeah.
And get
No, we just started this. To incorporate these branes, but you can put more of these branes. Started doing these interesting things.
I have a question about so I have a question about the contribution of the secondaries to the model. So if the secondaries can be any monolith, and if they do have to do a matrix model localization, or having to do localization.
So I think they will contribute, but this contribution will be not a leading order in N. So this is basically you get basically the twisted state there, but a leading order in N will be washed out. But yeah, there is a contribution of the matrix model, but it's not a leading order in N.
So we focus on the connectivity side of the story. How about the interior of the object? Can you say a little bit about how it'll go with it?
Good. So so this was done So in these two papers, last, what, 1 year ago, more or less, 1.5 years ago. So this was defined in these two papers. The M theory quotient. It's not an S-fold quotient in M theory. It's like another. It's another type of singularity. I think it's yeah. They study in particular singularities. I don't remember how they call it, but they call them. But it's not an S-fold in M theory. It's a Seyfried mod. It's a quotient singularity by discrete group. I don't remember exactly the detail of that, but it's in these two papers. So yeah, but the S-fold part is more the 2D side of the story. That's a good question. I don't remember. Yeah, it's I don't know whether they are isolated singularity. I don't remember. Yeah, I just don't remember now. but yeah, it's a yeah, it's a quotient of C3. I don't remember how the quotient was taken exactly, but that's as far as I remember. Yeah, it's a Calabi-Yau singularity. Yeah, yeah. I don't remember whether it's isolated. That's what I wanted to say.
So we're going to be resuming in 10:45. Let's thank